Good afternoon. Right now, this is a segment called Science. Let's take a look. It's every Tuesday, 12 to 1. I'm your host, Vince Gutschick, and we're going on a continuation of the show of last week, which was what makes a planet habitable. So we reviewed a number of things. First of all, just getting the temperature right at the planet. So stars come in all different sizes and lifetimes and temperatures, and planets likewise come in all kinds of sizes and distances from their stars, and also the regularity of their orbits and the way that they spin or don't spin. Maybe they're tidally locked. So you have to look at the energy balance of the planet. And maybe John will get a picture. John Nelson's here in the studio with me. You can, I'll just draw this picture. So, okay, let's put a sun here. Obviously not to scale. And let's put a planet over here. And so we've got the distance, the radius of the orbit, r. And if you consider different distances for the planet from the sun, you get a fall off of the radiation as 1 over the square of the radius. So if you're 3 times as far away, you get 1/9 as much radiation. The other thing is when you look at the total energy balance, the final temperature of the planet is really just how it exchanges radiation. There's no way to lose heat any other way. And that ends up being as the 4th power of the temperature. So if you work through the math, it says that the temperature falls off as 1 over the square root of that radial distance. So if you go to Mars, 52% further out from the sun than we are on average, it's about 20-some% lower in temperature. Everything else equal. Well, it's not exactly equal because Mars absorbs a little more radiation, but it also has a pretty wimpy greenhouse effect. So there's a number of other things that come in here. The other thing is you can't have the radius changing a lot as the planet orbits the sun. Let me get this out of the way. I'll just do this in black. So put the sun at the center. Our Earth is in a fairly circular orbit, meaning we say it's not very eccentric. The distance varies about 3%, but you can get planets that have a wide range of distances over their own year. And that means you get really hot here and really cold here. We're lucky that doesn't happen. Well, we wouldn't even consider being lucky. We wouldn't be here. Okay. That's good for that. So, thanks, John. The other thing that we talked about was getting the right elements on the planet. So where did those come from? The sun is a late starting star. So the universe is about 13.8 billion years old. The sun is 5 billion-ish, and that means that it is made up by condensation of things that were already made by other stars, a supernova or a merger of neutron stars, which was good because only then can you make the elements heavier than lithium, and we certainly rely on all those. You just name it: carbon, oxygen, manganese, iron, and so on. So we need about 20 elements, and they're here on the Earth. They're not equitably distributed, so that caused some interesting interactions. The other thing we covered is that carbon has to be the basis of life anywhere because it's the only one that makes stable bonds with itself and with all kinds of other elements. Silicon is an analog. People have talked about that. Silicon's too fat. Silicon atoms sit too far away from each other when they try to bond to make chains, so the bonds are weak. If you take the silicon analog of ethane called silane, Si2H6, it breaks into fire in the atmosphere with any oxygen. The other thing is people have said, oh, ammonia is an analog of water. We talked about this as being an isoelectronic species, same number of valence electrons. But it has a bad range of liquid to gaseous temperatures. So we skip that. Also would have a terrible greenhouse effect, runaway. And then you need an atmosphere to ameliorate the temperature and also to recycle some elements like nitrogen. And then there's more astronomical conditions, like the planet has to be able to rotate on its own as it goes around the star. So it can't be what we call tidally locked, always facing the star with one face, the way the moon faces us all the time with one face with tiny little librations around it. Also, the planet has to rotate fast enough on its axis. If it doesn't, you get freezing and baking conditions alternating over the long year. Okay. There's some things that we didn't cover yet on the astronomical and geological conditions, as I'm going to call them. That's distinct from what I call ecological conditions for habitability, which we'll address in a later show. I would guess we're not going to get through the other stuff here on the astronomical and geological side. So, one thing that was needed, as I mentioned, you had to have another star or a pair of stars create all of these heavier elements. So it had to be close to where the sun formed, but we don't want it to happen again close, or we'd be toast, literally. And the other thing, the sun has to be long-lived. Well, the sun is a type G star, sort of middling yellow star, temperature of about 5,800 Kelvin, about 10,000 Fahrenheit. And that makes it long-lived. It's about 5 billion years through its lifespan, probably has another 5 billion to go. It has changed how much radiation it puts out over the, well, it's not millennia. What do you call it? Anyway, that has caused some interesting things in the past that were intertwined with the rise of oxygenic photosynthesis that liberated enough O2 into the air to actually destroy the early greenhouse effect. But that was Snowball Earth, and we covered that last time. Another thing is you don't want the star, like our sun, to flare up. Yes, we do get flares from the sun, but they're not very big by the standards of many other stars. I mentioned earlier, well, that previous show, the star Proxima Centauri b, and it's one of a triplet of stars. It has a planet around it that looks Earth-like in size and so on. Although that star is pretty weak, it's very cool. It's only about 3,000 Kelvin instead of nearly 6,000 for our sun. In order to be warm enough, the planet has to be really close. It's 5% of our distance from the sun as its distance from its star. And that makes some interesting things. So initially people said, well, okay, if you do all the energy balance calculation, that could really work very well. It could be at a temperature a little cooler than us. But one of the big problems is it's a type of star that flares. And that has certainly blown away its atmosphere as well as cooked any life that was there. The mild flares that we get on Earth can really bother us. Mostly are